Okay, let's start now with an addition of the differentiator. PID has an integrator and a proportional block, but its D is indicating a differentiator. Now add differentiating or differentiator. A differentiator has an output which is proportional to the first derivative of the input. Yeah, if we have, don't forget, if we have a very simple block, x control difference input, y output, then this is a differential equation. Now I try to show you a graphical conversion into a digital algorithm. It works in the following very simple way. I make a diagram of the input signal, and yeah, maybe the curve looks like this, and if we are at the actual time t, say t1, then we know, okay, the derivative indicates the tangent gradient. It's a tangent, and the gradient of the tangent, slope of the gradient of the tangent, is exactly this xd over dt, the quotient dxt over dt. Okay, if we now sample the signal, then we have, say, here and here and here a sampling point. So this is the actual time point n, this is n minus 1, this is n minus 2. Then we have here xd of n, xd of n minus 1, and so on. So we have no chance to get the information of the gradient at this point. The ADC only gets the voltage, not the change of the voltage at this position. The only thing what a computer can do is look what gradient is coming up from the last sampling point to the new sampling point. So what we do is we replace gradient of the tangent or replace tangent with secant. And the calculation is very easy. We can say, okay, output y of n is n, the gradient here can be calculated by the vertical piece divided by the horizontal piece. The vertical piece from there to there is a difference between the actual value xdn minus the value one step before. And the horizontal difference between both points is our sampling time. Yeah, this is sampling time. So what we do is we replace replacing. This is a reason why this method I used in chapter 6 is called replacing differential equation by difference equation. Differential equation contains differential quotients, and we replace this with difference quotient. It's the difference between two time points, sampling times. It's the difference between voltage points. So we replace the derivative by a difference quotient ratio. Okay, let's look what happens now in our situation with PID controller. Back to our PID controller, we get the following equation. Note y of t now of my PID was k times, now the p part is coming, xd of t, plus the integral part is coming, 1 over ti integration from 0 to actual time, xd of t. That is my well-known pi part, but now we get the differentiation td multiplied with dxd of t divided by dt. This is the integration equation, the differential equation, we can say, of the PID. Note this is the equation for a PID. The pt1 time constant is 0, or that means that the step depth is infinity, has infinity large value. So this is the ideal PID. Note that we cannot realize this in hardware as an analog PID, and we want to check what happens now with the ideal PID converted into a digital algorithm. Okay, let's do all the things we have done in the previous chapters. We replace now the continuous time with sampled time points, and get then the yn is k times. In the proportional part we have no problem. We can replace the continuous time directly with the sampling time. In the integration we know that we have done this replacement by the sum of rectangles. I use, of course, my algorithm ending with the last rectangle, xd of I, plus now td, and you know what we have done just before, the differential quotient goes into the difference quotient. That means this is xd n minus xd n minus 1 divided by sampling time. Closing parenthesis gives the algorithm, we can call this algorithm a non-recursive algorithm, because the calculation of the output value doesn't need any other output values. But we know this cannot be programmed because the sum is appearing caused by the integration, so we have to go over to the recursive form, which comes now. Yeah, I show you now calculation way to recursive form to avoid the sum. You know, I call this equation 1, and I add a second equation where I can write down I make a copy of the complete algorithm by replacing now the n with n minus 1. So one step before, I have to calculate the following algorithm: k times xd of n minus 1 plus to divided by ti times sum from e to 0 times xd of e, but now ending with n minus 1, plus td times, now the difference also has to be calculated one step before, so this n becomes n minus 1, and this n minus 1 of course then becomes n minus 2 divided by t0, parenthesis closed. This is the equation copied, but one step before, and now I calculate, like I have done before, the difference of both equations, on the left side, I correct this at once by bringing the negative yn minus 1 on the right side. And now I put all values together, k, and I sort to xdn, all expressions with xdn I gather together in the first expression. So I look for this positive xdn. So I collect them and multiply with xdn. K times 1, this, plus the first element here. The only thing which remains if I look for the difference of both sums. All elements are equal, so reduced with subtraction. The only element which stays here is the t sub o divided by ti times xdn. And here we have also contribution of xdn, that is td divided by t0. So this is that what we call coefficient q sub o, the coefficient of the actual control difference the computer reads in this moment. But there are other parts of xd's that are all xd's with a minus 1, n minus 1. So this is covered, this is covered. But here you see we have a negative xdn minus 1. So negative td over t0 is the contribution of this. So I close this bracket and multiply with xdn minus 1. What have we more? Negative this value. Equation 2 is negative. So this is negative. So we have a negative 1 for this. Sum is gone. And here we have a negative xdn minus 1 times td over t0. So we have 2 times this element. And then there is no other value. And finally, we have here all things are covered in the first equation. In the second equation, we have only one missing part. This is the xdn minus 2. So plus k times td divided by t0 times xdn minus 2. We call this a coefficient of the input one step before. Traditionally is called q1, and the coefficient of the input value 2 steps before then gets the index 2. So in total we can say, okay, my PID recursive well-known famous algorithm can be written as new output yn can be calculated by using the old output. I have to store them, this value into a variable, plus multiplying q0 times the actual input control difference plus q1 times the control difference one step before. I have to store this value also in a variable, plus q2 times xd of n minus 2. So calculation need is 1, 2, 3 additions plus 3 floating point multiplications. In one step. So if I have a sampling time of say 1 millisecond, I have to do this 1000 mal a second, and this gives an indication for the processor load I need to calculate a PID control algorithm with a microprocessor. Okay, in the paper you can see on the bottom part of page 11, see this algorithm with the 3 Qs. On the next page in this paper, on page 12, top position, you can see how you have to calculate the 3 Qs if you have a PID T1 controller with known K, Ti, and Td. But in the paper, and I think not to make it into detail, you can also find variations of this algorithm, like a PD algorithm, without an integration. If you have no integration, you can do all the same steps, but note, and I want to show you now an overview table sorry, of all elements, which all variations of a PID algorithm which we can sum up. Here you see in the bottom row, you see the PID we have just done. These are the 3 Qs. This is a recursive design of a PID number Roman 1. We have discussed the P, we have discussed the PI, you see here. But note, here is a second P controller row. Why there are 2 forms of P controller. Here you see there is a non-recursive simple one we have done in the video, but there's also a recursive form. Of course, you can apply the trick with recursive form also for the P controller. Then you have the recursive one. Behavior of both is absolutely equal, but here you see we have 2 Qs. What a P is we discuss later. 3 Qs, 2 Qs, so we have to need 2 multiplications instead of 1. If the behavior is the same, the question is, why should we use a recursive P if a non-recursive has the same effect and less calculation power is necessary? The same is with PD. Look for the PD. I have skipped the chapter, but if you do this, there is a non-recursive and a recursive one. This is possible because the PD has no integrator. Note, the reason for recursive form was integration, because then this recursive form removes the very long sum. This is not necessary in the PD case. There is no integrator, there is no sum, so no need to remove this. So a non-recursive version of PD is possible. Of course, you can work with a recursive form. Some people do this, but I recommend to avoid this because this has 3 multiplications. The non-recursive form has 2 multiplications, so the computer has less load than recursive algorithm. But if there is an I here, pure I, PI or PID, of course then only a recursive form is available, because a non-recursive form with a very long sum cannot really be programmed. Okay, let's do an exercise example to investigate the PID behavior a little bit more. My calculation takes a PID controller with K2, Tn 1 second, TV 0.1 second, and I want to work with a sampling time of 10 millisecond, 0.01 second. Okay, let's do the exercise on paper. PID example. Given values are K is 2, Td is 0.1 second, Ti is 1 second, and sampling time is 0.01 second, 10 millisecond. Oh, sorry. Now I have to show you that this is not the example of the paper, because here you see I have different indices in the paper. So this is a good way to emphasize that we have to be careful about the indexes Tn and Tv. No, schon wieder falsch. Mist. Tn and Tv are given here in this way. TV is a small one, Tn is a large one, sampling time is 0.1 second. This is KC. Note, in English I often use KC, in German I sometimes use KR. Both parameters are exactly the same. The C comes from controller, the R comes from the German word Regler. In my paper, sometimes that is not absolutely clear which value I want to use. In the German version, I have some equations where I use the KR value. Okay, so far, go on. Because KC, TV, and Tn is given, and we need in my equations Ti, Td, and K, which are different, I have to convert them with conversion equations. C, conversion equations from workbook, from control system 1. Workbook, you have access to the workbook. Also the German students have access to the workbook, and I just make a copy of this equation here in this paper, and then I can use them. Okay, so in the workbook on page 21 you can find the conversion of the Bode form PID controller into the summing form PID controller, and the third form is the wiki form. I call this wiki form because this is used in the Wikipedia description of a PID controller. So there are different T's and K's. If you know one form, you should be able to calculate the other form. Look for this collection of equations. These are the 3 equations to convert the parallel form into the Bode form. These are the equations to convert the Bode form into the parallel form. These are the 6 equations to convert wiki form into parallel form, and with the others we can then convert into the Bode form. So in literature, all 3 forms do exist, so you have to work with all possibilities, and here are the ways to convert one into the other. We need these 3 equations, so I make a copy of this, put this into my writing, and then I can use these equations. You see, I've copied the 3 equations, so I can directly now put the values into these equations. K is 2 times, Tn is 1 second, 1 second plus 0.1 second divided by 1 second, so K is 2.2. Tn is just the sum of Tn and Tv, so Ti is 1.1 second, and Td is a multiplication 1 times 0.1 divided by the sum 1.1. So this is a time which is 0.090 period second. So this is a little bit larger than Tn, similar but larger, 10% larger. This is a little bit smaller than TV, so they are very near to each other but not the same, and K is a little bit larger than Kc. So these are now the parallel form params, and given are the Bode form params. This is important to know that controller design, or my controller design methods you have learned in workbook 1 in control system 1, throws out Bode form values. Our algorithm needs the parallel form values, so each time you have make a design in control system 1 of a PID controller, then you have to go through this conversion to get the parallel form parameters, and then you can put these values into the equations of my 3 Qs. So the next step is Q0 is K is 2.2 times 1 plus we have in the Q0 the sampling time 0.01 divided by 1.1 plus the TD is 0.090 period divided by sampling times 0.01, and you see this Q0 can be calculated as 1 plus a very small value, and this is a very large value. This is 9.09. This is 1, and this is a very small value in the region of 0.01. So this contains the integration information, this contains the differentiation information. Note that the sum here is the sum of a very large number and a very small number, and so in the computer we need sometimes high accuracy for our calculation, not to throw away the integration. I will show you an example later. So finally, if you factor out this is round about 9 plus 1 is 10, so round about 20.22 is a Q0 value. Q1 will be calculated to 42.20 if you put these values into the equations, and Q2 is exactly the value 20. So now we have the algorithm of our example is yn is yn minus 1, yn minus 1 plus Q0 is 22.22 times xd of n minus 42.2 xd of n minus 1 minus 20 times 0 times xd of n minus 2. A small exercise, please calculate for yourself by hand manually. Calculate manually the step response of this algorithm. That means xd is 1 starting with n0, and then go step by step through this algorithm. Then if you do this for yourself, then this may be a help. Solution comes up with the next video. Thank you for attendance. Bye bye.